You clicked on the world's most complex skybridge, but this isn't just a bridge. It's a structural system that forces entire skyscrapers to behave as one. You're looking at buildings that don't just stand. They transfer load, absorb motion, and share stress hundreds of feet above the ground. In Chongqing, one of these skybridges stretches over 1,000 feet long. That's longer than 3 football fields placed end to end. You heard that right. And it isn't supported from below. It's suspended between towers, carrying thousands of tons while resisting wind shear, thermal expansion, and seismic drift. That shouldn't be possible at this scale, because the moment you connect 2 skyscrapers in the air, everything changes. Each tower moves, each structure expands, each frame twists under load. And now, instead of solving one stable system, you're forcing multiple unstable systems to act like a single, rigid body. But this was just the beginning. Because before engineers could build the most complex skybridge on Earth, they had to prove one thing first: that separate buildings could survive being locked together in the sky. Linked hybrid network. You step into a cluster of towers that were never meant to stand alone. From the ground, they look like separate buildings, but the moment you rise high enough, you realize they've been locked together by a continuous loop of skybridges, wrapping around the entire complex like a rigid ring. At first, it seems simple. Connect multiple towers with elevated corridors. But the moment those bridges go in, the entire system stops behaving like individual structures. Each tower now carries not just its own load, but part of the load from everything connected to it. And that's where the problem begins. Because no 2 towers move the same way. Wind hits one facade harder than another. One tower expands under heat while another stays cooler in shadow. One shifts slightly under live load, while the others lag behind. These movements are small, sometimes just fractions of an inch, but at this height, that's enough to tear a rigid connection apart. So you're no longer designing buildings, you're designing relationships between buildings. Engineers had to solve this by allowing the skybridges to connect the towers without ever fully locking them in place. Expansion joints became critical. These weren't simple gaps, they were precision-engineered interfaces that allowed controlled movement while still transferring loads safely across the system. But that created a second problem. If the connections are too flexible, the bridges start to feel unstable. If they're too rigid, stress begins to accumulate at the joints, and that stress has nowhere to go. So the design had to find a balance rigid enough to feel solid, flexible enough to survive. Then came the issue of load distribution. Unlike a single building, where forces travel cleanly down into the foundation, this network introduced horizontal load paths. Weight from one tower could shift into another through the bridges. Wind forces could redistribute unpredictably across the loop. The entire structure became a dynamic system where forces didn't just go down, they moved sideways. And it wasn't just the structure that had to work. These skybridges weren't empty connectors, they were occupied spaces. People moving, gathering, adding live load that constantly changed throughout the day. That meant the system had to account for shifting weight in real time, without creating oscillations or discomfort. But this was just the beginning of the tension. Because building the system on paper was one thing, actually constructing it was something else entirely. Each tower was built separately, rising at slightly different speeds, under slightly different conditions. That meant, by the time the skybridges were ready to be installed, the towers were never perfectly aligned. And at this scale, even a small misalignment becomes a major problem. You're trying to connect structures hundreds of feet in the air, across gaps where even a minor deviation can prevent installation entirely. There's no forcing it into place, no room for error. So engineers had to build with anticipation. They predicted how each tower would settle under its own weight, how it would shift once fully loaded, how temperature would affect its height and position. Then they fabricated the bridges to match not where the towers were, but where they would be. That required an entirely different level of precision. When the time came to install the skybridges, everything had to align within extremely tight tolerances. Cranes lifted massive sections into place, while engineers monitored movement in real time, adjusting positioning down to the smallest measurable increments. And when the final connections were made, something changed. The towers stopped behaving like separate structures. For the first time, they began to act as a single interconnected system, sharing load, redistributing stress, stabilizing each other through the very connections that once threatened to pull them apart. That was the breakthrough. You weren't just linking buildings anymore. You were teaching them how to work together. But if this system proved that multiple towers could be connected, the next project pushed the idea even further, because instead of creating a loop between buildings, engineers decided to turn the entire structure into one massive frame and carve a hole straight through the middle of it. Gate to the east. You're no longer looking at separate towers connected by bridges. This time, you're standing inside a single structural frame. Two vertical legs rising into the sky, joined by a massive horizontal section that locks them together at the top. It looks clean, symmetrical, almost simple, but structurally, it's anything but. Because the moment you carve a void between two towers and connect them at the top, you create one of the most unstable configurations imaginable. Instead of each tower carrying its load straight down into the ground, forces now have to travel up, across, and back down again. That horizontal connection, the skybridge, isn't just a link. It's a load-bearing beam at extreme height, and everything depends on it. You're dealing with enormous bending forces concentrated at the top of the structure. Gravity is constantly trying to pull that horizontal span downward, while the towers beneath are forced to resist not just vertical loads, but the inward pull created by that span. The entire system wants to deform. The top wants to sag, the legs want to bend inward, and wind only makes it worse. At this height, wind doesn't just push, it creates oscillation. One tower may deflect slightly before the other, introducing uneven forces into the skybridge. That imbalance feeds back into the system, amplifying stress at the connection points. So now you're not just holding weight, you're controlling motion. Engineers had to design the upper section as a rigid structural element capable of redistributing these forces across the entire frame. This meant reinforcing the skybridge with deep structural members, essentially turning it into a massive beam that could resist bending while staying stable under constantly changing loads. But even that wasn't enough, because the structure couldn't be completely rigid. If it were, stress would build up at the joints where the horizontal and vertical elements meet. Over time, that stress could lead to material fatigue or worse, failure. So just like before, the solution wasn't pure strength, it was controlled flexibility. The connections had to allow micro-movements, small shifts, that release stress without compromising the integrity of the overall frame. That balance between stiffness and flexibility became the defining challenge of the entire project. But this was just the beginning of the real problem. Because designing the structure was one thing, building it in the air was something else entirely. Unlike a traditional skyscraper, where each floor stacks directly on top of the one below, this project required constructing two massive towers first, then connecting them at the very top with extreme precision. And those towers didn't rise in perfect sync. Small differences in construction speed, material behavior, and environmental conditions meant that by the time they approached their final height, they were never perfectly aligned, not in position, not in elevation, not even in how they responded to load. But the skybridge had no tolerance for that. It had to fit exactly. So engineers had to predict how both towers would behave not just during construction, but after completion. They calculated how much each tower would compress under its own weight, how wind would influence its position, how temperature changes would cause expansion and contraction. Then they built the connection piece to match a future state that didn't yet exist. You're essentially trying to hit a moving target hundreds of feet in the air. When the time came to install the top section, the margin for error was razor thin. Massive components were lifted into place, while engineers tracked alignment in real time, adjusting for deviations that could mean the difference between success and complete failure. There was no forcing it into position. If it didn't align, the entire system would be compromised. But when the final connection locked in, something remarkable happened. The structure stabilized. The two towers, which once behaved independently, began to resist forces together. The horizontal span started redistributing loads, reducing stress concentrations, and reinforcing the entire frame. What once looked like a fragile void became a source of strength. That was the shift. You weren't just connecting buildings anymore. You were using the connection to redefine how the entire structure carried load. But even this had limits. Because this system still relied on a clear, predictable geometry, a frame, a span, a defined load path, the next project abandoned that simplicity completely. Because instead of stabilizing a structure with a single connection, engineers started stretching entire buildings sideways, turning skybridges into something far more dangerous. 10-cent skybridge system. You're no longer moving up a building, you're moving across it. At 10-cent's headquarters in Shenzhen, the idea of a skybridge stops being a connection and starts becoming the building itself. Multiple towers rise independently, but instead of being capped by a single link, they're stitched together by long horizontal volumes that stretch across the skyline. This isn't a bridge you cross. It's a space you inhabit, and that changes everything. Because the moment a skybridge becomes occupied at this scale, it stops behaving like a connector and starts acting like a fully loaded structural element. Offices, equipment, people, every pound adds to a span that's already fighting gravity, wind, and its own geometry. These horizontal sections aren't short links. They're long span structures suspended between towers, carrying massive loads while remaining stable enough for daily use. And unlike vertical towers, which naturally channel forces downward, these elements must resist bending across their entire length. So the deeper you look, the more fragile it starts to feel. Because these spans want to sag, they want to deflect under their own weight, they want to twist under uneven loading. And when wind moves through the complex, each tower responds differently, pulling and pushing against the very spans that connect them. Now you're not dealing with one moving structure. You're dealing with multiple moving anchors tied together by something that cannot afford to move too much. That's the tension. To solve this, engineers turn to mega-truss systems, deep structural frameworks embedded within the horizontal volumes. These trusses act like the spine of the skybridge, distributing loads across the span while maintaining stiffness against bending and torsion. But even with that, the problem doesn't disappear. Because stiffness creates its own risk. If the system is too rigid, differential movement between towers transfers directly into the horizontal spans. That introduces stress concentrations that can build over time, especially under repeated wind loading or thermal expansion. And at this scale, thermal expansion isn't minor. Steel and concrete expand and contract with temperature changes, and across long spans, that movement adds up. What seems like a small shift at one end becomes a significant displacement across the entire structure. So once again, engineers had to design for movement. Connections between towers and skybridges were carefully detailed to allow controlled displacement, absorbing expansion, contraction, and slight misalignments without compromising structural integrity. But this balancing act created another layer of complexity, because now you're allowing movement in a structure that people occupy. If the system moves too much, occupants feel it. Floors can vibrate. Spaces can feel unstable. And that's not just uncomfortable, it's unacceptable. So engineers had to control not just structural safety, but human perception. They tuned the stiffness of the system to limit perceptible movement, while still allowing enough flexibility to prevent stress buildup. Every decision became a trade-off between stability and adaptability. But the real challenge came during construction. Because these weren't isolated towers built independently, they were part of a system that had to come together with extreme precision. Each horizontal section had to align perfectly between towers that were still settling, still shifting, still responding to their own weight and environment. And the longer the span, the smaller the margin for error. You're lifting massive structural components into place, hundreds of feet in the air, trying to connect them across gaps where even a slight deviation can make installation impossible. So engineers relied on staged construction. Temporary supports, incremental assembly, and constant monitoring allowed them to adjust positioning in real time. They tracked how each tower moved during the process, compensating for deviations before final connections were made. It wasn't just about building, it was about synchronizing. And when the final sections locked into place, the system transformed. What once felt like separate towers connected by fragile spans became a continuous horizontal structure, rigid where it needed to be, flexible where it had to be, and stable enough to function as a single environment. That was the breakthrough. The skybridge was no longer a link, it was the backbone. But even this system still followed a kind of logic: linear spans, predictable connections, controlled geometry. The next project shattered that completely, because instead of connecting towers with straight lines, engineers created a structure that loops back into itself, where the bridge doesn't just connect the building, it completes it. CCTV, loop structure. You're standing inside a building that refuses to behave like one. There's no clear top, no simple vertical rise. Instead, the structure bends, angles, and then does something that feels almost impossible. It connects back into itself, forming a continuous loop suspended in the air. At first glance, it looks like two leaning towers joined by a skybridge, but that's not what this is. This is a closed structural circuit, and the moment that loop is completed, everything changes. Because now, loads don't just travel down, they circulate. Gravity pulls forces through angled columns, across the overhanging sections, and back into the ground through a completely different path. Every part of the structure depends on every other part. There's no redundancy in the traditional sense, only interdependence. And that's where the danger begins. Because until the loop is closed, the structure is incomplete. Each tower leans, each section cantilevers outward. Massive portions of the building extend into space, unsupported except by the strength of their internal framing. These overhanging elements are under constant stress, fighting against gravity with no final load path to stabilize them. So during construction, you're not building a finished system. You're holding together something that isn't stable yet. That creates enormous tension, because the most critical moment of the entire project comes down to a single phase closing the loop, bringing two massive, independently constructed sections together in midair and locking them into a configuration that finally allows the structure to behave as designed. But nothing lines up perfectly at this scale. Each section has already deformed under its own weight. Steel has flexed, concrete has settled, wind has pushed the structure in subtle, unpredictable ways. Even temperature differences across the site can shift alignment. So when those two ends approach each other, they're never exactly where you want them to be, and there's no room for force. If you try to push them into alignment, you introduce stress that can ripple through the entire system. At this level of complexity, that's not just risky, it's catastrophic. So engineers had to do something far more precise. They predicted deformation before it happened. Using advanced modeling, they calculated how each section would behave under load, how it would bend, twist, and settle as construction progressed. Then they built each segment slightly offset, intentionally misaligned, so that by the time they reached the closing phase, everything would fall into place. You're not building to match reality. You're building to match a future state. And when the time came to close the loop, the margin for error was almost non-existent. Massive steel sections were maneuvered into position with microscopic precision relative to their size. Adjustments were made slowly, carefully, constantly monitored. Because this wasn't just another connection. This was the moment the entire structure either worked or failed. Then came the most critical instant of all, the final connection, locked in. And suddenly, the behavior of the building changed. The overhanging sections, once under extreme stress, found their load paths. Forces began to redistribute through the loop, stabilizing areas that had been vulnerable during construction. What once felt like a collection of unstable parts became a unified structural system. The building stopped fighting itself. It started supporting itself. But the complexity didn't end there, because this looped geometry introduced another challenge torsion. Unlike straight structures, where forces are relatively predictable, this irregular form created twisting effects throughout the frame. Wind hitting one face could introduce rotational forces that traveled through the entire loop, amplifying stress in unexpected areas. So engineers had to reinforce the structure to resist not just bending but twisting. Every joint, every connection, every structural member had to account for forces coming from multiple directions at once. This wasn't a building you could simplify. It had to be understood as a system. And that system had to perform flawlessly, because once completed, there was no isolating failure. Everything was connected. Everything mattered. That was the leap. You weren't just connecting towers. You were creating a structure where the connection was the structure. But even this level of complexity still operated within a closed system. One building, one loop, one continuous frame. The next project broke even that boundary, because instead of forming a loop within a single structure, engineers stretched a massive enclosed skybridge across multiple skyscrapers, turning separate towers into a single horizontal megastructure suspended in the sky. Raffles City Skybridge. You're not looking at a bridge anymore. You're standing inside a horizontal skyscraper suspended in the air, stretched across multiple towers, carrying the weight of an entire building where no building should exist. They call it the Crystal. It stretches over 1,000 feet long. That's longer than 3 football fields placed end to end. You heard that right. And it isn't supported from below. It's suspended between towers, hundreds of feet above the ground, forcing separate structures to behave like one coordinated system. But the moment you try to understand how it works, the scale stops feeling impressive and starts feeling unstable, because this isn't one tower rising from a foundation. This is multiple towers, each moving differently, each responding to wind, heat, and load in its own way, all locked together by a single continuous structure that cannot afford to fail. Every tower sways, every column shortens under weight, every surface expands and contracts with temperature. And now you're forcing all of that movement into one shared system. That shouldn't work. Because if even one tower drifts out of sync, the stress doesn't disappear, it transfers directly into the skybridge. And across a span this long, even tiny shifts can amplify into something dangerous. So the challenge wasn't just holding the bridge up, it was controlling everything beneath it. Engineers had to design a system that could stay stable while the towers it relied on were constantly shifting. That meant creating connections that didn't just support load, but managed movement. And at the core of it all was a massive steel mega-truss. This wasn't a hidden support. This was the structure. Running through the entire length of the skybridge, it acted like a rigid spine carrying load across the span and distributing forces back into the towers. Every section fed into it, every tower depended on it. But that created tension, because the stiffer that spine became, the more sensitive it was to movement from the towers. And at this height, movement is unavoidable. So the connections had to do something almost contradictory. They had to keep the bridge secure, without locking it in place. Each connection point was engineered to allow controlled movement. Just enough to absorb tower sway, thermal expansion, and structural drift without letting stress build up inside the system. But this was just the beginning. Because the longer the structure, the more it reacts to temperature. One side heats up in direct sunlight and expands. Another stays cooler and contracts. Across a span this large, that difference creates internal forces strong enough to damage the structure unless they're managed. So the bridge had to breathe. Expansion joints and sliding interfaces were built into the system, allowing it to adjust in real time, expanding, contracting, shifting slightly without losing stability. But then came a problem you can't see, only feel. Wind moves through the towers, vibrations travel into the bridge. Small oscillations begin to build, not enough to cause failure, but enough that people inside would notice. And that's where control became critical. Engineers installed tuned mass damper systems designed to counteract movement by shifting weight in the opposite direction. As the structure begins to sway, these dampers respond instantly, absorbing energy and stabilizing the motion. So you're not just keeping the structure standing, you're controlling how it behaves, how it feels. But the most difficult part wasn't designing it, it was building it. Because this structure couldn't be assembled in one place. Massive sections were prefabricated on the ground, huge, heavy, and built to exact specifications. Then they were lifted into the air and installed across towers that were still moving, still settling, still changing. And at this scale, there is no margin for error. You're connecting pieces across hundreds of feet, where even the smallest misalignment can stop everything. So once again, engineers had to predict the future. They calculated how each tower would compress under its own weight, how it would shift over time, how wind and temperature would change its position. Then they built the skybridge for where the towers would be, not where they were. You're aligning a structure to a moving target, and there's no second attempt. As each section was lifted into place, alignment was monitored in real time. Adjustments were made down to the smallest, measurable increments. Every connection had to land perfectly, not just physically, but structurally. Because if one segment locked in wrong, the entire system would feel it. Then came the moment everything depended on. The final connections. The last sections were positioned. The structure closed. The load paths completed. And instantly, everything changed. The towers, once moving independently, began stabilizing each other through the bridge. Forces started redistributing across the entire system. Movement didn't stop, it balanced. What looked like separate skyscrapers became something else entirely. One structure, one system, one continuous form suspended in the air. And the bridge, the part that should have been the weakest, became the reason it all works. Because at this level, you're not just building taller, you're building across the sky and making it hold.